Everything you think you know about the universe rests on one single number. That number is wrong, and we have no idea what that means. A number baked into the fabric of reality itself. A number so fundamental that if it's wrong, our entire picture of the universe collapses. Scientists have spent 100 years measuring it. Satellites, supercomputers, the greatest minds in human history, all chasing this one single value. And they found it. Twice. Using completely different methods, completely different technology, completely different teams on opposite sides of the planet. The answers should have matched. They didn't. And nobody can explain why. This isn't a small discrepancy. This isn't a rounding error buried in a footnote somewhere. This is a 5 sigma crisis. In physics, that's the equivalent of dropping a ball and watching it fall up. It means something is either catastrophically broken in our math, or something is out there in the universe that we have never seen, never measured, and never even imagined. Then the James Webb Space Telescope pointed itself at the problem. The most powerful observatory ever launched, a machine so precise it can see light that has been travelling toward us since before the Earth existed. It looked, it measured, and instead of solving the crisis, it deepened it. Right now, physicists are quietly losing sleep over this. Because if the gap is real, and it's looking more and more like it is, then the standard model of cosmology, the story we tell about how this universe was born, how it grew and where it's going, might be fundamentally catastrophically incomplete. Now, before we go any further, I genuinely want to know where you're watching this from. Are you curled up somewhere at home, lights low, the world quiet outside? Or are you in the middle of a city, surrounded by noise and light, stealing a few minutes for something that actually matters? Tell me in the comments. I read them. Every single one. And if you're the kind of person who watches a video like this, who chose to spend time on a mystery this big, do me a favour and hit subscribe, because this channel exists for exactly you. For the people who look up at the sky and feel that pull, that quiet, unsettling feeling that the universe is so much stranger than anyone is letting on. It is. Get comfortable. Turn the volume up, because what we're about to get into doesn't just challenge a number, it challenges everything. Let's begin. The universe is getting bigger. Not in the way a balloon inflates into the room around it. Because there is no room around the universe. Space itself is stretching. Every cubic metre of vacuum between galaxy clusters is quietly expanding, adding new distance where none existed a moment ago. The effect is too small to detect in a living room or a solar system, but across millions of light years, the cumulative stretch becomes enormous. Distant galaxies are racing away from us, not because they are moving through space like cars on a highway, but because the road between us and them is growing longer while they sit still. This is not intuitive. Human beings evolved to understand movement as objects travelling from one place to another. A cheetah runs across the savannah. A baseball flies toward a catcher's mitt. A rocket climbs away from a launch pad. All of these involve things moving through a fixed arena of space. Cosmic expansion is fundamentally different. The arena itself is growing. The galaxies are not sprinting away from us. They are sitting relatively still while the fabric of reality between us inflates, stretching every photon of light, widening every gap, adding distance that did not exist a heartbeat earlier. If this seems strange, it should. Nothing in daily experience prepares you for it. This expansion has a speed, or more precisely, it has a rate, and that rate is captured by a single number called the Hubble constant, named after Edwin Hubble, the American astronomer who first confirmed in 1929 that galaxies outside our own are moving away from us in every direction. The Hubble constant tells you something deceptively simple. For every megaparsec of distance between you and a distant galaxy, 1 megaparsec equals roughly 3.26 million light-years. Space expands by a certain number of kilometres every second. That is it. One number. One rate. It should be the same whether you measure it by looking at the ancient universe or the nearby universe. It should be the same whether you use exploding stars, pulsating giant stars, the afterglow of the Big Bang, or the gravitational bending of light around massive galaxies. The Hubble constant is supposed to describe a property of the cosmos as a whole, not a local quirk. It should converge. It does not. This is not a new problem. Astronomers have been arguing about the Hubble constant for nearly a century, but the nature of the argument has changed. In the early decades, the disagreements were enormous. Hubble's original estimate placed the expansion rate at roughly 500 kilometers per second per megaparsec, a number so high it implied the universe was younger than the Earth. Clearly, something was wrong. Over the following decades, astronomers realized that Hubble had used the wrong calibration for his Cepheid distance measurements. The Cepheids he observed in distant galaxies were classical Cepheids, bright young population 1 stars. But the period luminosity calibration he applied came from observations of fainter population 2 Cepheids in globular clusters. Since population 2 Cepheids are intrinsically dimmer than classical Cepheids at the same pulsation period, using the wrong calibration made galaxies appear closer than they actually were, inflating the measured expansion rate. Walter Baades' discovery of these 2 distinct stellar populations in the 1940s corrected this error and roughly doubled the cosmic distance scale. This confusion compressed his distance estimates, making galaxies appear much closer than they actually were. When you underestimate distance but correctly measure recession velocity, the implied expansion rate skyrockets. Corrections brought the number down dramatically. By the 1960s, 2 camps had formed. One group, led by Alan Sandage, who had been Hubble's protege at the Mount Wilson Observatory, argued for a value near 50 kilometers per second per megaparsec. Another group, led by the French-born astronomer Grade de Vaucouleurs, argued for a value near 100. The disagreement consumed careers and generated feuds that lasted decades. Sandage and de Vaucouleurs clashed publicly at conferences, each accusing the other of systematic errors in their methodology. The dispute became one of the most bitter and protracted in 20th century astronomy. The problem was not laziness or incompetence. Measuring cosmic distances is extraordinarily hard. You cannot stretch a tape measure to another galaxy. You cannot bounce radar off a star cluster 100 million light-years away. Instead, you build a chain of increasingly uncertain measurements, each one resting on the one below it. Measure the distance to nearby stars using parallax, the tiny shift in a star's apparent position as Earth orbits the Sun. Use those stars to calibrate the brightness of a certain class of pulsating stars called Cepheid variables. Use those Cepheids to measure distances to nearby galaxies. Use those galaxies to calibrate the brightness of Type 1a supernovae. Use those supernovae to measure distances across billions of light-years. Each link in this chain is called a rung on the cosmic distance ladder, and every rung introduces a small uncertainty that compounds as you climb higher. The genius of the distance ladder is its logic. Each rung overlaps with the one above it and the one below it, creating a continuous chain from Earth's backyard to the far reaches of the observable universe. But its weakness is also clear. An error at the bottom propagates upward through every subsequent rung. Miscalibrate the Cepheids, and every distance built on top of them shifts. Misjudge the intrinsic brightness of a Type 1a supernova, and billions of light-years of distance measurement tilt in one direction. The ladder is only as trustworthy as its weakest rung. For decades, the uncertainties in the distance ladder were large enough to accommodate either camp. The true Hubble constant could have been 50 or 100, or anywhere in between, because the error bars overlapped. Nobody could prove their answer was right, and nobody could prove their opponent was wrong. Then, technology improved. The Hubble Space Telescope, launched in 1990, was designed in part to settle this debate. Orbiting above Earth's blurring atmosphere, it carried instruments capable of resolving individual Cepheid variable stars in galaxies tens of millions of light-years away, something ground-based telescopes struggled to do. A dedicated project called the Hubble Key Project, led by astronomer Wendy Friedman, spent years observing Cepheids in dozens of galaxies, carefully calibrating the distance ladder rung by rung. The team observed roughly 800 Cepheids across 18 galaxies, building the most comprehensive distance calibration the field had ever seen. By the year 2001, they published a definitive result, 72 kilometers per second per megaparsec, with an uncertainty of about 10%. The feud seemed to be ending. The number had landed in the middle of the old debate, and most astronomers accepted it. The Hubble constant appeared settled. Textbooks were updated. Review articles declared the problem essentially solved. Cosmology appeared to be entering a precision era where the big questions were answered and only the decimal places remained. Then a completely different way of measuring the expansion rate matured, and the crisis began. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as Double Map. Its first major results, published in 2003, did not look at stars or galaxies. It stared at the oldest light in the universe, the cosmic microwave background radiation. A faint glow permeating all of space, left over from a time roughly 380,000 years after the Big Bang. At that moment, the universe had cooled enough for the first atoms to form, and light was able to travel freely for the first time. That ancient light has been travelling ever since, stretched by cosmic expansion into microwave wavelengths. It fills the sky in every direction, like a fading echo of creation. The cosmic microwave background is not perfectly uniform. It contains tiny temperature fluctuations, variations of only a few hundred thousandths of a degree, that correspond to slight density differences in the early universe. These fluctuations are the seeds that eventually grew into galaxies and galaxy clusters through gravitational collapse over billions of years. The pattern of these fluctuations encodes an enormous amount of information about the universe's composition, geometry, and expansion history. By analysing this pattern with extraordinary precision, cosmologists can calculate what the Hubble constant should be today, given what the universe looked like when it was an infant. The method works because the physics of the early universe is remarkably well understood. Before atoms formed, the universe was a hot plasma of charged particles and radiation. Sound waves, oscillations of pressure driven by the competition between radiation pressure pushing outward and gravitational attraction pulling inward, rippled through this plasma at roughly half the speed of light. These sound waves left a characteristic imprint on the density pattern, creating peaks and troughs at specific angular scales in the cosmic microwave background. The position and height of these peaks depends sensitively on the universe's composition, how much ordinary matter, how much dark matter, how much dark energy, and how fast space was expanding. Measure the peaks precisely, and you can extract the cosmological parameters with extraordinary accuracy. WOMAP produced a value of approximately 71, consistent with the Hubble Key project. Everything seemed fine. But then came Planck. The European Space Agency's Planck satellite, launched in 2009, observed the cosmic microwave background with far greater sensitivity and angular resolution than DUTMAP. It mapped the temperature fluctuations across the entire sky with precision that was almost absurd, measuring temperature differences of just a few millionths of a degree across millions of independent patches of sky. When the Planck team analysed their data using the standard cosmological model, a framework called lambda CDM that describes the universe as composed of ordinary matter, cold dark matter and dark energy in the form of a cosmological constant, they calculated a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. 67.4, not 72, not 73. 67.4. At first the discrepancy seemed like a statistical hiccup. Measurement uncertainties exist in every experiment. Maybe one side had underestimated their errors, maybe a subtle calibration issue would eventually be uncovered. But the gap did not close. It widened. On the other side of the debate, a team called SHOW-S Supernova H-Nero for the Equation of State, led by Nobel laureate Adam Riess at Johns Hopkins University, had been systematically improving the cosmic distance ladder for over a decade. They used the Hubble Space Telescope to observe Cepheid variable stars in galaxies that also hosted Type 1 supernovae. By anchoring the distance ladder with multiple geometric calibrations, parallaxes from the Gaia spacecraft, eclipsing binaries in the Large Magellanic Cloud, water masers in the galaxy NGC 4258, they drove down their uncertainty to less than 2%. Their most refined measurement landed at 73.04 kilometers per second per megaparsec. 73 versus 67, a difference of roughly 9%. Both measurements were spectacularly precise. Both had been checked and rechecked by independent groups around the world, and the gap between them had reached a statistical significance of 5 sigma, meaning the probability that this discrepancy was caused by random chance was less than 1 in 3.5 million. In particle physics, 5 sigma is the threshold for declaring a discovery. It is the standard that was used to announce the detection of the Higgs boson in 2012. In cosmology, reaching 5 sigma signaled something potentially far more consequential, a crack in the foundation of the Standard Model. This discrepancy earned a name, the Hubble tension, not the Hubble disagreement or the Hubble inconsistency. Tension, because it pulls at the fabric of modern cosmology from 2 directions simultaneously. On one side, the early universe tells us the expansion rate should be 67. On the other, the nearby universe insists it is 73. Both cannot be right, unless something in our understanding of the universe is missing, incomplete, or wrong. The tension is not about sloppy measurements. That is the part that unsettles cosmologists most deeply. If one measurement were clearly less reliable than the other, the community would simply wait for better data and move on. But both methods are grounded in well-understood physics. Both have been scrutinized by dozens of independent teams. Both have survived every systematic check that has been thrown at them. The data are excellent. The data disagree. This is the crisis. The Hubble constant should be constant. It should not depend on when in cosmic history you measure it or which method you use. The expansion rate derived from the infant universe and the expansion rate measured in the mature universe should converge on a single value, because they describe the same physical reality. Yet they produce 2 answers separated by a gap too large to ignore and too persistent to explain away with known errors. What makes this especially maddening is that the standard model, lambda CDM, has been one of the most successful theoretical frameworks in the history of science. It accurately predicts the temperature fluctuations in the cosmic microwave background down to fractions of a percent. It explains the observed abundance of light elements, hydrogen, helium, deuterium, lithium, forged in the first few minutes after the Big Bang through a process called primordial nucleosynthesis. It describes how galaxies cluster into the vast cosmic web of filaments and voids that telescope surveys have mapped across billions of light years. It accounts for the accelerating expansion of the universe driven by dark energy, a discovery that won the 2011 Nobel Prize in Physics. Lambda CDM is not a rough sketch. It is a precision instrument that matches observations across 13.8 billion years of cosmic history with remarkable accuracy. Except for this one number. The Hubble tension sits like a splinter in the framework, small enough to be dismissed by some, painful enough to demand attention from others, and persistent enough to suggest that something important might be hiding just beneath the surface of our most successful cosmological model. To understand why this matters, you need to appreciate what the Hubble constant actually controls. It is not just an abstract rate, it determines the age of the universe. A faster expansion rate means the universe reached its current size in less time, making it younger. A slower rate means it took longer, making it older. The Planck value of 67 implies the universe is approximately 13.8 billion years old. The Schnurrier's value of 73 implies the universe could be closer to 12.7 billion years old. That difference of roughly a billion years creates immediate conflicts with observations of the oldest stars, some of which appear to be nearly 13 billion years old, based on stellar evolution models and white dwarf cooling sequences. Stars cannot be older than the universe that contains them. If the higher expansion rate applies globally, something in our understanding of stellar ages or cosmic chronology must give. The Hubble constant also affects our understanding of dark energy, the mysterious force driving cosmic acceleration. It influences calculations of the total matter density in the universe, the formation timeline of the first galaxies, and the predicted size of the sound horizon. The characteristic scale imprinted in the cosmic microwave background by sound waves in the early universe change the Hubble constant, and ripple effects cascade through every cosmological calculation. The size of the observable universe shifts. The predicted abundance of galaxy clusters at different epochs adjusts. The inferred properties of dark matter halos surrounding galaxies change. No parameter in cosmology is truly independent. They form an interconnected web, and tugging on one thread, the Hubble constant, pulls on all the others. This is why the tension refuses to remain a quiet academic disagreement. It touches everything. And this is where the James Webb Space Telescope enters the story. Launched on December 25, 2021, from a European Space Agency launch site in French Guiana aboard an Ariane 5 rocket, Webb carried instruments designed to see the universe with a clarity and depth that no previous telescope could match. Its primary mirror, 6.5 meters across and composed of 18 hexagonal, gold-coated beryllium segments, collects light with a sensitivity that dwarfs the Hubble Space Telescope. Positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth, shielded from solar radiation by a sun shield the size of a tennis court, Webb operates at temperatures close to minus 233 degrees Celsius. Its infrared instruments can peer through dust clouds that blind optical telescopes, resolve individual stars in distant galaxies with unprecedented sharpness, and detect faint objects at the edge of the observable universe. Webb was not built specifically to resolve the Hubble tension. Its mission encompasses everything from imaging the atmospheres of exoplanets to observing the first galaxies that formed after the Big Bang. But among its many capabilities is one that matters enormously for the expansion rate debate: the ability to observe Cepheid variable stars and other distance indicators with far greater precision than any instrument before it. At infrared wavelengths, Webb's angular resolution surpasses Hubble's by a factor of roughly 2 to 3. This means that stars which appeared as smeared blobs in Hubble images can be cleanly separated and individually measured by Webb. For a field that depends on knowing the precise brightness of individual stars in crowded galactic environments, this improvement is transformative. The question hanging over the Hubble tension for years had been simple and uncomfortable. Could the disagreement be caused by a subtle error in the distance ladder that better instruments would reveal? Or would sharper observations confirm that the tension is real, forcing cosmologists to confront the possibility that something fundamental is missing from the standard model? Webb pointed its mirror at the sky. The data came back. And the answer pleased no one. Before moving forward, it is worth pausing on what the shock really is here. It is not that Webb found some magical new phenomenon. It is not that a fundamental constant has been proven to change. The shock is quieter and more methodical than that. Careful independent measurements of a supposedly stable number, the rate at which the universe expands, are not lining up, and the most precise telescope ever built has just confirmed that the disagreement is not going away. The next step is understanding exactly how each measurement works, why both are so trustworthy, and why that trustworthiness is precisely what makes the disagreement so alarming. To understand why the Hubble tension is so stubborn, you need to understand how each measurement works, not in vague terms, but precisely enough to appreciate why neither side can easily dismiss the other. These are not two groups of scientists guessing. They are two groups using fundamentally different physics, applied to fundamentally different epochs of cosmic history, and arriving at answers that should be identical but are not. One group reads the baby picture of the universe and calculates what the expansion rate must be today. The other group walks outside, measures nearby galaxies directly, and records what the expansion rate actually is today. The methods share almost no assumptions, almost no instruments, and almost no sources of error. They are as independent as two measurements in cosmology can possibly be. And they disagree. Start with the cosmic microwave background method. This approach does not measure the expansion rate directly. Instead, it measures the conditions of the early universe with extraordinary precision, and then calculates what the expansion rate must be today if the standard cosmological model is correct. It is an inference, not a direct observation, but the inference rests on physics that has been tested and confirmed across multiple independent lines of evidence, which is why cosmologists trust it so deeply. Recall the cosmic microwave background, the ancient light released when atoms first formed, roughly 380,000 years after the Big Bang. Part of the story was how that light was freed. Now the question is what it encodes, because the Planck satellite did not simply detect this radiation, it dissected it. It mapped temperature fluctuations across the entire sky with a sensitivity capable of detecting differences of a few millionths of a degree. The resulting map shows a pattern of hot and cold spots at various angular scales, some spanning several degrees of sky, others just fractions of a degree. These spots are not random noise. They encode the physics of the early universe, the density of matter, the density of radiation, the balance between gravity and pressure in the primordial plasma, the geometry of space, and the rate at which the cosmos was expanding when atoms first formed. Before atoms formed, sound waves rippled through the hot plasma, the same oscillations described earlier, driven by the competition between radiation pressure and gravitational collapse. What matters here is what those oscillations left behind. The sound waves created a characteristic scale in the density pattern. This scale depends on how far sound could travel before the universe became transparent. Essentially, the distance a sound wave could cover during the first 380,000 years of cosmic history. That distance, called the sound horizon, is approximately 147 megaparsecs in today's expanded universe, or roughly 480 million light-years. It represents a fixed physical scale, a cosmic ruler baked into the structure of the universe by the physics of the primordial plasma. The angular size of this sound horizon as seen in the cosmic microwave background depends on two things: the physical size of the ruler and the distance to the surface where the light was emitted. That distance depends on how the universe expanded between recombination and today. By measuring the angular positions of peaks in the power spectrum of temperature fluctuations, a mathematical decomposition of the hot and cold spots into their component spatial frequencies, cosmologists can determine with remarkable precision the total matter density, the baryon density, the dark energy density, the optical depth to reionization, the spectral index of primordial fluctuations, and the expansion rate. The Planck team, using the lambda CDM model with 6 free parameters, obtained a Hubble constant of 67.4 plus or minus 0.5 kilometers per second per megaparsec. The uncertainty is less than 1%. This is not an approximation or an educated guess. It is a precision measurement derived from the physics of the universe when it was less than 1,000th of its current age, processed through a theoretical framework that has successfully predicted dozens of independent observations. There is a subtlety here that matters enormously. The Planck measurement of the Hubble constant is model-dependent. It assumes that lambda CDM correctly describes the universe from recombination to the present day. If the standard model is exactly right, then the Planck value is the true expansion rate. But if something about the standard model is incomplete, if dark energy evolves, if additional particles existed in the early universe, if gravity behaves differently on cosmological scales, then the Planck-derived Hubble constant could shift. The measurement of the cosmic microwave background itself is superb. What could be wrong is the theoretical framework used to interpret it. This distinction will become important later. Now consider the second method, the cosmic distance ladder. The distance ladder, the chain of measurements from geometric parallax through Cepheids to Type Ia supernovae, was introduced earlier. Now it is time to examine each rung closely enough to see why the method is so hard to dismiss. The challenge lies not in the concept, but in the calibration. Astronomers call objects with known intrinsic luminosity standard candles, though the term is slightly misleading because no astronomical object has a perfectly constant, universally known brightness. Instead, Standard candles are objects whose brightness can be determined through some observable property, a pulsation period, a spectral feature, a light curve shape that correlates reliably with luminosity. The most important standard candles for the Hubble constant are Cepheid variable stars and Type Ia supernovae. Once you have the distance, combine it with the object's redshift, how much the wavelength of its light has been stretched by cosmic expansion, and you can calculate how fast space is expanding at that distance. Cepheid variables are giant stars that pulsate in brightness with clock-like regularity. They swell and contract, heating and cooling as they do so, creating a rhythmic variation in luminosity that repeats over periods ranging from a few days to several months. In 1912, Henrietta Swan Leavitt, a human computer working at the Harvard College Observatory, discovered that the period of a Cepheid's pulsation is directly related to its intrinsic luminosity. A Cepheid that pulses every 30 days is intrinsically brighter than one that pulses every 10 days, following a tight mathematical relationship. Measure the pulsation period, something you can do from any distance as long as you can detect the star, and you know the true brightness. Compare it to the apparent brightness, and you get the distance. Leavitt's discovery, published initially as a brief note about stars in the Small Magellanic Cloud, became one of the most consequential findings in the history of astronomy. This period luminosity relation makes Cepheids invaluable for measuring distances out to tens of millions of light-years. They are bright enough to be detected individually in galaxies well beyond our own, and their pulsation periods can be measured through repeated observations over weeks or months. But Cepheids are not bright enough to be seen across billions of light-years. Even the most luminous Cepheid would be too faint to detect at cosmological distances. For that, you need something far more luminous. Type Ia supernovae fill that role. These are thermonuclear explosions of white dwarf stars that reach a remarkably consistent peak brightness. A white dwarf is the dense, Earth-sized remnant of a dead star, composed primarily of carbon and oxygen. When a white dwarf in a binary system accumulates enough mass from its companion star to approach the Chandrasekhar limit, approximately 1.4 solar masses, or when two white dwarfs spiral together and merge, the result is the same. The white dwarf can no longer support itself against gravitational collapse. Carbon fusion ignites throughout the star in a runaway thermonuclear explosion that completely destroys the white dwarf. The explosion, which unfolds in a matter of seconds, briefly outshines its entire host galaxy, producing luminosities roughly 5 billion times that of the Sun. The peak luminosity of these explosions, after applying corrections for how quickly they brighten and fade, a property captured by the width of the light curve, is remarkably standardizable. Brighter Type I supernovae take longer to fade. Dimmer ones fade faster. This relationship, discovered in the early 1990s by astronomer Mark Phillips, and often called the Phillips relation, transforms Type I supernovae from merely bright objects into calibrated distance markers. Once calibrated, they can be observed across billions of light-years, making them the most powerful distance probes in the astronomer's toolkit. They are the same objects whose observations in 1998 led to the discovery that the universe's expansion is accelerating, a finding that earned the 2011 Nobel Prize in Physics. The distance ladder works by linking these two candles through a bridging strategy. Observe Cepheids in nearby galaxies whose distances you already know through geometric methods, parallax measurements from the Gaia spacecraft, eclipsing binary star systems in the Large Magellanic Cloud whose orbital physics yield a direct distance, or water maser emissions from accretion disks around supermassive black holes in galaxy centers. These geometric methods provide the first rung, absolute distances calibrated without any assumptions about stellar brightness. Use those geometrically anchored Cepheids to calibrate the period luminosity relation with high precision. Then observe Cepheids in more distant galaxies that also happen to host Type Ia supernovae. The Cepheids give you the distance to these host galaxies. The supernovae in those same galaxies provide the calibration. Now you know the absolute luminosity of a Type Ia supernova. Finally, use those calibrated supernovae to measure distances to far more distant galaxies, where Cepheids are invisible, out to redshifts where cosmic expansion dominates over local motions. Each rung of the ladder is a measurement. Each measurement introduces uncertainty. The art of precision cosmology lies in controlling those uncertainties at every step. The geometric anchors must be accurate. The Cepheid period luminosity relation must be universal, or its environmental dependencies must be understood and corrected. The Type 1 supernova standardization must work across different types of host galaxies. Dust between the observer and the target can dim and redden the light, mimicking greater distance. Unresolved stars blended with the Cepheid target can make it appear brighter, mimicking shorter distance. Every potential bias must be identified, quantified, and corrected. The Shura's team has spent more than 15 years refining this ladder with meticulous care. They have anchored the base with geometric distances to 3 independent calibrators, the Large Magellanic Cloud, measured through eclipsing binaries and Cepheid parallaxes, the Galaxy NGC 4258, measured using water masers orbiting its central black hole, and the Milky Way's own Cepheids, measured using Gaia satellite parallaxes. Each anchor provides an independent check on the others. They have observed Cepheids in over 40 galaxies that also hosted Type 1 supernovae, building a large statistical sample that reduces random errors. They have applied corrections for dust reddening using multi-wavelength observations, chemical composition differences between Cepheids in different galactic environments, and photometric blending, the contamination of Cepheid brightness measurements by unresolved neighbouring stars that fall within. The same point spread function of the telescope. Their result? 73.04 plus or minus 1.04 km per second per megaparsec. The uncertainty is about 1.4%, 73 from the local universe, 67 from the ancient universe, a 6 km per second per megaparsec gap that neither team can explain away. Both teams have published extensive analyses of their error budgets, both have invited outside scrutiny, both have responded to criticisms with additional tests and cross-checks. The measurements have not converged, they have solidified. But the story does not stop with 2 methods. Several other independent techniques have weighed in over the past decade, and their results scatter across the tension rather than resolving it. Each method brings its own physics, its own assumptions, and its own sources of uncertainty. Together they paint a picture that is more complex and more troubling than a simple 2-sided disagreement. The tip of the red giant branch method, known as TRGB, uses a different type of standard candle entirely. When low-mass stars similar to or slightly less massive than the Sun, exhaust the hydrogen in their cores, they undergo dramatic structural changes. Their cores contract and heat up, while their outer envelopes expand enormously, turning them into red giants. As a red giant evolves, it ascends the red giant branch on the Hertzsprung-Russell diagram, growing progressively more luminous as its core temperature rises. Eventually, the core reaches approximately 100 million degrees Kelvin, hot enough for helium to begin fusing into carbon through the triple alpha process. This ignition happens suddenly and violently, a thermonuclear runaway called the helium flash. The helium flash occurs at a nearly uniform luminosity, regardless of the star's chemical composition or initial mass. The tip of the red giant branch, the maximum brightness a star reaches just before the helium flash, serves as a standard candle. Identify the brightest red giants in a galaxy's halo, measure their apparent brightness at the tip, and you have a distance. The physics behind this uniformity is well understood. The helium flash is triggered by a specific core temperature threshold, which translates to a specific luminosity. The TRGB method has practical advantages over Cepheids. Red giant branch tip stars are found in the halos of galaxies, the diffuse outer regions where stellar crowding is less severe and dust contamination is lower. They do not require time series observations, because you are measuring a single brightness threshold, not a pulsation period. They are old, evolved stars found in virtually every galaxy, providing broad applicability. Some TRGB measurements have produced Hubble constant values around 69 to 70, intriguingly positioned between the Planck and Schichtenau-Iez values, as though the universe was splitting the difference. Others have yielded values closer to 72 or 73, depending on the calibration sample and the colour corrections applied. The disagreement among TrueGB analyses themselves stems from differences in how the tip luminosity is calibrated, which anchor galaxies are used, how extinction corrections are applied, and how the tip is identified in colour magnitude diagrams that can be noisy and ambiguous. The TrueGB has not settled the tension. It has added a third voice to the conversation, one that sometimes whispers compromise and sometimes shouts in agreement with the distance ladder. Baryon acoustic oscillations provide yet another approach, one that is conceptually elegant and largely independent of both stellar candles and the cosmic microwave background. These are the fossilized imprints of the same sound waves that created the peaks in the cosmic microwave background. After atoms formed and the sound waves froze, the characteristic scale, the sound horizon, remained permanently embedded in the distribution of matter. The slight overdensities at the sound horizon scale survived gravitational evolution and persist today in the clustering pattern of galaxies. Think about what this means in physical terms. The same sound waves that created the peaks in the cosmic microwave background had a spatial consequence that persists today. Each initial overdensity in the early universe launched a spherical pressure pulse outward through the plasma, carrying baryonic matter with it, while the dark matter at the centre, unaffected by radiation pressure, stayed put. When recombination occurred and the universe suddenly became transparent, the radiation pressure vanished. The sound wave stalled. The baryonic matter that had been riding the wavefront was left stranded in a shell at the sound horizon distance, the same 480 million light-year ruler already encoded in the cosmic microwave background. The result was two concentrations of matter, one at the original centre where the dark matter remained, and one in a shell at the sound horizon distance where the baryonic matter had been deposited by the frozen wave. Over the next 13 billion years, gravity amplified both concentrations. Galaxies formed preferentially at the original centres and along the shells. The result, imprinted across the entire observable universe from billions of independent initial overdensities, is a subtle but unmistakable statistical preference. Galaxies are slightly more likely to be separated by roughly 480 million light-years than by other distances. The sound waves that rang through the universe in its first few 100,000 years left permanent scars in the arrangement of galaxies across the sky. Frozen ripples in the cosmic architecture that serve as one of the most powerful distance tools in modern cosmology. Measuring this preferred separation in galaxy surveys at different redshifts gives a standard ruler, not a standard candle, but a known physical length that can be compared across cosmic epochs. The ruler does not depend on understanding stellar physics. It depends on understanding plasma physics in the early universe, which is well constrained by the cosmic microwave background itself. By measuring the apparent angular size and redshift space length of this ruler at different distances, astronomers can map the expansion history of the universe across billions of years, tracing how the expansion rate changed as matter diluted and dark energy rose to dominance. Baryon acoustic oscillation measurements from surveys like the Sloan Digital Sky Survey and the more recent dark energy spectroscopic instrument tend to produce Hubble constant values more consistent with Planck, in the range of 67 to 68, though with larger individual uncertainties than either. Planck, or Esch-Nero-Iez. This is perhaps not surprising, since baryon acoustic oscillations rely on the same sound horizon calibration as the cosmic microwave background analysis. If the sound horizon is correct, baryon acoustic oscillations and Planck should agree. If something about the early universe changed the sound horizon from its expected value, if new physics shrank the ruler before it was frozen, then both methods would be affected in the same direction, both underestimating the true Hubble constant by the same amount. This correlated vulnerability is important. Baryon acoustic oscillations and the cosmic microwave background are not fully independent tests of the expansion rate. They share a common foundation, and if that foundation is slightly wrong, they would be wrong together. Gravitational lensing time delays offer yet another independent check, one rooted in general relativity rather than stellar physics or plasma dynamics. The concept is almost cinematic in its strangeness. When a massive galaxy or galaxy cluster lies along the line of sight to a distant quasar, one of the brightest persistent objects in the universe, powered by a supermassive black hole consuming matter at a prodigious rate, the gravitational field bends light along multiple paths, creating multiple images of the same quasar arranged in arcs, crosses, or rings around the lensing mass. Each image corresponds to a light path that traverses a slightly different route through the curved spacetime around the lens. One path might arc above the lensing galaxy, another curves below it. A third might thread through a gap in the mass distribution. Each path has a slightly different total length and passes through regions of slightly different gravitational potential, introducing time delays governed by general relativity. When the quasar varies in brightness, as quasars frequently do, flickering unpredictably as clumps of gas spiral into their central black holes and release bursts of radiation, the variation appears in each image at a slightly different time. One image brightens on a Monday, another shows the same brightening event on a Thursday, a third catches up the following week. By monitoring all images simultaneously over months or years, astronomers can measure these time delays with precision of a day or better. The delays, combined with a detailed model of the lensing galaxy's mass distribution, yield a quantity called the time delay distance, a combination of angular diameter distances between observer, lens, and source that is directly and geometrically sensitive to the Hubble constant. The technique converts a time measurement into a distance measurement using gravity as the intermediary, bypassing stars, supernovae, and the cosmic microwave background entirely. The Hochschlakow and TD Cosmo collaborations have used this technique on several lensed quasar systems, carefully modelling the lens mass distributions using high-resolution imaging from the Hubble Space Telescope, spectroscopic data from ground-based telescopes, and dynamical measurements of stellar motions within the lensing galaxy. Their early results, based on 6 lensed quasars, favoured values around 73, consistent with the distance ladder. However, the accuracy of this method depends critically on the assumed mass profile of the lensing galaxy. The total mass enclosed within a given radius determines how much the light is bent and delayed. If the mass profile is assumed to follow a simple power law distribution, density decreasing smoothly from centre to edge, the resulting Hubble constant is well constrained. But when the TD Cosmo team relaxed this assumption, allowing for more complex internal structures such as a distinct stellar core embedded in a broader dark matter halo, or accounting for additional mass concentrations along the line of sight from foreground and background galaxy groups that contribute their own lensing effects, the uncertainties expanded significantly, enough to be consistent with either camp. The gravitational lensing method remains one of the most promising avenues for an independent resolution, particularly as Webb and future 30-metre class ground telescopes improve lens modelling. But it has not yet achieved the precision needed to break the deadlock. Surface brightness fluctuation methods, which measure the graininess of unresolved starlight in elliptical galaxies as a distance indicator, have contributed measurements consistent with the higher end of the tension. Megamaser cosmology, using the geometric distances to water masers orbiting supermassive black holes, has provided anchor distances for the distance ladder. Gravitational wave standard sirens, measuring the distance to neutron star mergers independently through gravitational wave amplitude, represent perhaps the most exciting emerging technique. When 2 neutron stars spiral inward and collide, the gravitational waves they emit carry information about their distance that is completely independent of any electromagnetic observation. The amplitude of the gravitational wave signal encodes the luminosity distance directly. No standard candles, no standard rulers, no cosmic microwave background, no assumptions about stellar physics or dust or metallicity, just the pure geometry of spacetime rippling under the collision of 2 compact objects. The first standard siren measurement from the binary neutron star merger JW170817, detected in 2017, produced a Hubble constant of roughly 70, with uncertainties too large to distinguish between camps. But as gravitational wave detectors improve in sensitivity and accumulate dozens or hundreds of events over the coming decade, standard sirens may ultimately deliver the cleanest measurement of the Hubble constant that science can produce, one that owes nothing to any other method and shares no systematic vulnerabilities with any existing technique. The picture that emerges from this constellation of methods is not one of two measurements disagreeing while everything else agrees with one side. It is a landscape of measurements that scatter across the tension, clustering loosely around either the high end or the low end, with none providing a decisive resolution, and the clustering follows a pattern that demands attention. This is what makes the Hubble tension so difficult. If there were a single outlier measurement contradicting everything else, the community would focus on finding the error in that outlier. But the tension is structural. Methods that rely on early universe physics, the cosmic microwave background, baryon acoustic oscillations, consistently favour the lower value, around 67. Methods that measure the expansion rate directly in the nearby universe, Cepheids, supernovae, gravitational lensing, surface brightness fluctuations, consistently favour the higher value, around 73. The division follows a pattern. Early universe methods land low, late universe methods land high, and patterns demand explanation. Some researchers have proposed that the disagreement is not about the expansion rate at all. Perhaps the early universe methods are correct about conditions at recombination, and the late universe methods are correct about local expansion, but something happened between these two epochs that changed the effective expansion rate. If the universe underwent a brief period of additional acceleration in its early history, caused by a component of energy that was active before or during recombination, but faded away well before the present, it could shrink the sound horizon, shifting the Planck inferred Hubble constant upward, without disrupting the cosmic microwave background fit in other ways. This is the essence of early dark energy proposals, which have attracted significant theoretical attention. Others have suggested that the late universe measurements are subtly contaminated by our local environment. If the Milky Way sits inside a large underdense region of space, a cosmic void where the local matter density is lower than the cosmic average, then galaxies within this region would experience less gravitational deceleration and would appear to recede faster than the cosmic average. This would inflate the locally measured Hubble constant, making it higher than the true global value. This hypothesis, sometimes called the local void explanation, has been studied extensively using galaxy surveys and peculiar velocity measurements. While there is evidence for a modest local underdensity, most analyses suggest it is not large enough or deep enough to fully account for the 6 km per second per megaparsec gap. It might contribute a kilometre or two, but not 6. Still, others have examined the possibility that the standard model itself needs modification in ways that affect the relationship between early universe observables and the present-day expansion rate. Perhaps dark energy is not a cosmological constant, but a dynamical field whose equation of state evolves over time. Perhaps additional species of neutrinos or other light particles existed in the early universe, increasing the radiation energy density and altering the expansion rate before recombination. Perhaps gravity behaves differently on cosmological scales than general relativity predicts, changing the relationship between the geometry of the cosmic microwave background and the expansion rate today. Each proposal has consequences that extend far beyond the Hubble constant. Each introduces new parameters into the cosmological model. Each must be tested not only against the Hubble tension, but against every other cosmological observation simultaneously: the cosmic microwave background power spectrum, the abundance of light elements, the growth rate of cosmic structure, the clustering of galaxies, the properties of the cosmic. Webb. Any solution that fixes the Hubble constant but breaks something else is not a solution, it is a trade, and each proposal needs better data to test. That is where the James Webb Space Telescope came in. Not as a theoretical arbiter, not as a discoverer of new physics, but as a measuring instrument of unprecedented precision, capable of testing whether the distance ladder's lowest rungs, the rungs most vulnerable to systematic error, had been built correctly. If Webb could confirm or deny the Cepheid-based distances with sharper instruments and cleaner photometry, it would either validate the high local value or reveal an error that had been hiding in the data for years. The stakes were clear. If Webb found that Cepheid measurements from the Hubble Space Telescope were contaminated by blending, dust, or calibration issues, the tension might dissolve. The local Hubble constant would drop closer to 67. The standard model would be vindicated, and cosmologists could sleep soundly. But if Webb confirmed the Hubble Space Telescope measurements, if sharper images produced the same distances and the same expansion rate, then the systematic error escape hatch would close. The tension would harden from a possible measurement problem into a probable physics problem. Before we move on, re-anchor on the core point. The shock here is not a dramatic headline. It is that the most carefully measured quantity in observational cosmology, the expansion rate of the universe, gives different answers depending on how you measure it. The early universe says 67. The nearby universe says 73. Multiple independent methods line up on each side. The tension is not between sloppy estimates. It is between some of the most precise measurements in the history of science. And the next chapter shows what happened when the sharpest telescope ever launched looked directly at the problem. The James Webb Space Telescope did not enter the Hubble tension debate with a theory. It entered with a mirror and the sharpest infrared vision ever deployed beyond Earth's atmosphere. Webb was not designed as a cosmological referee. Its mission portfolio spans everything from sniffing the atmospheres of rocky exoplanets to capturing the faint light of galaxies that formed when the universe was barely 200 million years old. But among its capabilities is one that became immediately relevant to the most uncomfortable problem in modern cosmology: the ability to cleanly separate individual stars in distant crowded galaxies where every previous observatory saw only smeared light. Webb's primary advantage for the expansion rate debate was not its size alone, but its infrared sensitivity combined with angular resolution. Those two capabilities working in tandem address specific vulnerabilities in the cosmic distance ladder that had haunted Cepheid measurements for decades. To understand why this matters, you need to understand a problem that sounds mundane but carries enormous cosmological consequences. That problem is crowding. Here is the situation Webb was built to resolve. When the Hubble Space Telescope observed Cepheid variable stars in distant galaxies, the galaxies that also hosted Type 1a supernovae, the critical overlap zone where the distance ladder connects its second and third rungs, it observed them primarily in optical and near-infrared wavelengths. Cepheids are bright stars, but they do not exist in isolation. They live in galaxies teeming with millions of other stars. In the disk of a spiral galaxy where star formation is active, the stellar density can be extraordinary. Thousands of stars may crowd into a region that a telescope sees as a single smeared point of light. At optical wavelengths, the Hubble Space Telescope's resolution, roughly 65 milliarseconds in its best filters, was good enough to identify Cepheids in relatively nearby galaxies. But as the distance increased to 20, 30, 40 megaparsecs and beyond, the angular separation between stars shrank below Hubble's ability to distinguish them. Individual Cepheids began to blend with their neighbours. This blending created a contamination problem that was subtle but insidious. Nearby stars, unresolved by Hubble's optics, contributed extra light to the Cepheid measurement. This made the Cepheid appear slightly brighter than it actually was. A brighter apparent magnitude, when compared to the known intrinsic luminosity from the period-luminosity relation, implies a shorter distance. A shorter distance to the host galaxy means a higher inferred recession velocity per unit distance, and a higher recession velocity per unit distance means a higher Hubble constant. The bias was systematic. It always pushed in one direction. Blending always adds light. It never subtracts it. Added light always makes the target appear closer than it really is. Blending had always been a concern within the Shoei's collaboration. The team applied careful statistical corrections based on artificial star tests, a technique where simulated Cepheids of known brightness are injected into real Hubble images of the target galaxies, and their recovered brightness is compared to the input value. The difference between input and output reveals how much the local crowding environment biases the photometry. These corrections were sophisticated and well tested, refined over multiple iterations spanning more than a decade of Hubble observations. But they depended on assumptions. Assumptions about the crowding environment, how many faint stars lie below the detection threshold and contribute unresolved light, assumptions about the point spread function of the telescope, the precise shape of the blur pattern that determines how far a star's light spreads across the detector, assumptions about the luminosity distribution of background stars in different galactic environments, which varies from galaxy to galaxy. Critics argued that residual blending effects might still be inflating the local Hubble constant, not by enough to explain the entire 6 km per second per megaparsec tension perhaps, but enough to shave 2 or 3 off the top, bringing the local value down to 70 or 71, and reducing the statistical significance of the disagreement from 5 sigma to something less alarming. If blending corrections were underestimated by even a small amount, the entire edifice of the high local measurement could be subtly tilted. This was not an unreasonable criticism. Photometric blending in crowded fields is a genuine challenge in observational astronomy. It has affected measurements in other contexts, stellar population studies in globular clusters, photometry of stars in the galactic bulge, brightness measurements of variables in the Magellanic Clouds. The concern was legitimate. What was missing was a definitive test. This is where Webb's capabilities became decisive. At infrared wavelengths spanning roughly 1 to 5 microns, the F90W, F150W, and F277W filters aboard Webb's near-infrared camera, known as NIRCam. Webb's angular resolution is roughly 2 to 3 times sharper than Hubble's at the same wavelengths. The improvement comes from Webb's larger primary mirror, which produces a smaller diffraction limited point spread function. In practical terms, 2 stars separated by 40 milliarcseconds that Hubble would see as a single blob, Webb can split into 2 distinct points of light. This is not a marginal improvement, it is a qualitative change in what the telescope can see. For Cepheid photometry, this meant that Webb could separate individual Cepheids from their neighbours in crowded fields, where Hubble saw only a single blurred source. The contamination that blending introduced could be measured directly by comparing the Cepheids' brightness in Webb's clean, resolved image to the brightness that Hubble had recorded in its blurred image, rather than estimated statistically through artificial star simulations. If Hubble's blending corrections had been wrong, Webb would reveal it immediately. The brighter-than-expected Cepheids in Hubble data would appear fainter and more accurate in Webb data. The distances would increase, the Hubble constant would drop. In 2023, the first Webb observations specifically targeting the Hubble tension were published. The SH0ES team, working in collaboration with Webb instrument scientists and the broader astronomical community, observed Cepheid variables in 2 galaxies that are critical anchors for the upper rungs of the distance ladder, NGC 5584 and NGC 4258. Both galaxies had previously been observed extensively by Hubble. NGC 4258 is particularly important because it serves as one of the 3 geometric anchors of the distance ladder. Its distance is known independently through water maser observations, providing an absolute calibration point for the Cepheid period luminosity relation without any dependence on other standard candles. NGC 5584 hosted a well-observed Type 1a supernova in 2007 and contains a rich population of Cepheid variables that the SH0ES team had measured with Hubble over multiple observing epochs. Together, these 2 galaxies represent precisely the links in the chain where blending could do the most damage if it existed, one anchoring the bottom of the ladder, the other connecting Cepheids to supernovae at the critical bridging rung. The results were striking in their precision rather than their surprise. Webb's sharper images confirmed that the Cepheid brightness measurements made by Hubble were not significantly biased by blending. The photometric scatter, the spread in brightness measurements from star to star at a given pulsation period, dropped by a factor of roughly 2 compared to Hubble observations. This reduction in scatter is exactly what you would expect if Webb is resolving sources that Hubble was blurring together. Individual Cepheids that had been marginal detections in Hubble data faint, noisy, sitting on a messy background, became clean, unambiguous measurements with Webb. Stars that Hubble could barely separate from their surroundings stood out clearly against resolved backgrounds. The crowding corrections that Hubble had required, sometimes amounting to a few tenths of a magnitude, were largely unnecessary with Webb, because the stars were now cleanly isolated. But here is the critical finding. When the Webb-based Cepheid distances were plugged into the distance ladder, the resulting Hubble constant remained at approximately 73 km per second per megaparsec. The error bars tightened, the central value barely moved, the scatter decreased, the precision improved, and the answer stayed the same. The tension persisted, now measured with even greater confidence. This was not the answer many cosmologists had hoped for. A significant portion of the community, perhaps even a majority of theorists working on the tension, had been quietly betting that Webb would reveal a systematic error in the Cepheid measurements. The expectation was understandable. Throughout the history of astronomy, discrepancies between measurements have almost always turned out to be systematic errors rather than new physics. The conservative assumption is always that someone made a mistake. Webb was supposed to find the mistake. It did not. Webb eliminated the blending hypothesis with clinical precision. Whatever is causing the Hubble tension, it is not Cepheid blending in the Hubble Space Telescope data. The brightness measurements that Hubble made over 15 years of careful observation, measurements that critics had questioned, scrutinized, and proposed as the source of the discrepancy, turned out to be correct. Two different telescopes, separated by a generation of engineering, operating at different wavelengths with different detectors and different optical properties, produced the same Cepheid distances. But Webb's contribution extended well beyond confirming Cepheid measurements. The telescope also turned its infrared eyes toward tip-of-the-red giant branch stars, the Trögby distance indicators that offered an entirely independent alternative to Cepheids on the second rung of the distance ladder. Webb's infrared sensitivity gave it a decisive advantage for Trögby measurements, because red giant branch tip stars are cool, evolved objects that emit the bulk of their radiation at wavelengths longer than 1 micron. Hubble could observe these stars in its reddest filters, but Webb sees them in their native spectral territory, where they are brightest and where photometric measurements are most reliable. Trögby measurements had been a source of both hope and confusion in the tension debate for years. The method was championed by several groups, most prominently a team led by Wendy Friedman at the University of Chicago, the same astronomer who had led the original Hubble Key project 2 decades earlier. Friedman's group reported Trögby-based Hubble constant values closer to 69.8, tantalizingly positioned between the Planck value of 67 and the Schröers value of 73, as though the universe were diplomatically splitting the difference. If the Trögby result was correct, the tension might not require new physics at all. Perhaps the Cepheid distances were slightly biased upward, the Planck value slightly biased downward, and the true expansion rate sat comfortably in between at a level of disagreement that fell below the threshold of crisis. Other groups, however, using different calibration choices and different approaches to colour corrections, obtained Trögby values closer to 72 or 73, in agreement with the Cepheid-based ladder rather than splitting the difference. The disagreement among Trögby analyses themselves added a layer of confusion on top of the existing tension. The community was not just debating Cepheids versus the cosmic microwave background, it was debating Cepheids versus Trögby versus the cosmic microwave background, with the Trögby results depending sensitively on choices that different groups made differently. The discrepancy between Trögby analyses largely came down to technical choices in how to calibrate the tip luminosity and how to correct for the effects of stellar metallicity, the abundance of elements heavier than helium in the stars being measured. The Trögby luminosity is remarkably uniform, but it is not perfectly so. Stars with higher metallicity have slightly different opacities in their outer envelopes, which shifts their colour and, depending on the photometric band used for measurement, can subtly affect the apparent brightness of the tip. Different groups apply different metallicity corrections, use different anchor galaxies to set the 0 point, and employ different algorithms to identify the tip in colour magnitude diagrams that can be noisy. particularly in galaxies where the red giant population is sparse. Webb's observations helped clarify this by providing significantly cleaner photometry of Trigby stars in host galaxies of Type 1a supernovae. The sharper images reduced scatter in the colour magnitude diagrams and allowed more precise identification of the tip luminosity. Background contamination from unresolved faint stars, a problem analogous to blending in Cepheid measurements, though typically less severe in the sparser halo environments where Trigby stars reside, was measurably reduced by Webb's superior resolution. Early Webb-based TRGB analyses produced values broadly consistent with the Cepheid ladder. The exact numbers depended on which calibration strategy was employed, but certain calibration choices that had previously produced low Hubble constant values from the TRB became harder to justify with the improved Webb photometry. The error bars tightened, the range of plausible TRB results narrowed, and the narrowed range tilted toward the higher end of previous estimates rather than the lower end. Webb did not deliver a final verdict on the TRGB debate. The community continues to work through calibration differences, but it constrained the space of possibilities in a direction that intensified rather than relaxed the tension. Beyond Cepheids and TRGB stars, Webb contributed to the tension debate through observations of a newer distance indicator, the J-region asymptotic giant branch method, known as JAG. This technique uses carbon-rich stars at a specific stage of stellar evolution as standard candles. When intermediate mass stars exhaust helium in their cores, they ascend the asymptotic giant branch, a phase of stellar evolution characterized by intense luminosity and dramatic mass loss through stellar winds. A subset of these stars develop carbon-rich atmospheres through a process called dredge-up, where convective mixing brings carbon produced by helium fusion from the stellar interior to the surface. These carbon stars have a characteristic near-infrared luminosity in the J-band, approximately 1.2 microns, that is remarkably uniform and can serve as a distance indicator. The JAG method is relatively new compared to Cepheids and TRGB, but it has attracted attention because it operates at wavelengths where Webb excels, and because it provides a third independent check on the distance ladder. Webb's infrared capabilities made it an ideal instrument for detecting and measuring JAG stars in distant galaxies where ground-based infrared telescopes lacked the resolution, and space-based optical telescopes lacked the wavelength coverage. Early JAG-based distance measurements derived from Webb data have yielded Hubble constant values consistent with the higher end of the tension, around 71 to 73. Though the method is still being refined, its systematic uncertainties are still being characterized, and its calibration sample is still growing. The collective impact of Webb's observations across all three distance indicators can be summarized in a single uncomfortable statement. Every systematic error that critics proposed as an explanation for the high local Hubble constant has been tested by Webb, and none of them have been confirmed as significant. Blending does not explain it. Cepheid photometric errors do not explain it. Trigby calibration discrepancies do not clearly resolve it. JAG measurements corroborate rather than contradict the Cepheid result. Each time Webb sharpened a measurement, the high local value held firm. Each time a proposed systematic was tested with better data, the proposed systematic failed to materialize at the level needed to resolve the tension. This does not mean the tension has been proven to reflect new physics. It is important to be precise about what Webb has and has not demonstrated. Subtle systematic effects could still lurk in places Webb has not yet examined. The absolute calibration of the distance ladder's first rung, the geometric anchors, relies on Gaia parallaxes for Milky Way Cepheids, the eclipsing binary distance to the Large Magellanic Cloud, and the maser distance to NGC 4258. These geometric foundations have their own uncertainties and modelling assumptions that Webb does not directly test. If the Gaia parallax 0 point contains a small systematic offset, it would propagate through every Cepheid distance built on top of it. If the Large Magellanic Cloud distance is slightly wrong, every calibration anchored to it shifts in lockstep. Webb sharpened the upper rungs of the ladder, but did not rebuild the base. Metallicity corrections for Cepheids remain an active area of debate. The period luminosity relation may depend on the chemical composition of the Cepheid in ways that are not yet fully characterized. Different host galaxies have different average metallicities, and if the metallicity dependence is steeper or shallower than currently assumed, the resulting distances would shift, not by much, perhaps 1% or 2%. But in a debate where the tension amounts to roughly 9%, even small shifts matter. Dust-reddening models may contain inaccuracies that affect both Cepheid and TIRGB measurements in subtle, correlated ways. If the properties of interstellar dust, grain size, distribution, composition, wavelength-dependent extinction vary from galaxy to galaxy more than current models assume, the distance corrections could harbour biases that Webb's resolution improvement alone cannot reveal. But the space of plausible systematic explanations has narrowed significantly since Webb began observing. Before Webb, it was scientifically reasonable to hypothesize that the high Hubble constant from the distance ladder was an artifact of Hubble Space Telescope limitations, blending in crowded fields, photometric artifacts from an aging detector, insufficient resolution to cleanly separate Cepheids from their environments. After Webb, that entire category of explanation carries dramatically less weight. The data from 2 different telescopes, using different instruments at different wavelengths with different optical properties and different systematic vulnerabilities, agree on the local expansion rate. Concordance between independent instruments is one of the strongest forms of evidence in observational science. When 2 fundamentally different measurement systems produce the same answer, the answer is probably real. This tightening of systematics is actually what makes Webb's contribution so important and so deeply unsettling for the field. Webb did not discover a new particle. It did not detect an unexpected signal from the edge of the universe. It did not produce a headline-grabbing image that rewrote cosmological models overnight. It did something far more methodical, and in some ways far more consequential. It confirmed that one side of the Hubble tension is not making an obvious mistake. And by doing so, it shifted the burden of explanation from the observers to the theorists. If the late universe measurements are correct and free of significant systematic bias, then either the early universe measurements are wrong, which would require errors in the Planck satellite data, or fundamental flaws in the lambda CDM model used to interpret them, or the standard model of. Cosmology is genuinely incomplete. Since the Planck data have been scrutinized exhaustively by multiple independent teams around the world, reanalyzed with different pipelines and different foreground models, and found to be internally consistent and robust, the implication tilts increasingly toward incompleteness in the theoretical framework rather than error in the observations. Webb also contributed to the broader cosmological conversation through its deep field observations of galaxies at high redshifts, observations that were not designed to address the Hubble tension, but that generated findings with indirect relevance. Several studies using Webb data reported finding massive structurally mature galaxies at cosmic times earlier than the standard model comfortably predicted. Initial estimates suggested galaxies with stellar masses exceeding 10 billion solar masses had appeared at redshifts of 7, 8, even 10, corresponding to times when the universe was only a few 100 million years old. Some of these mass estimates have since been revised downward as photometric analyses improved, but several cases have held up under scrutiny, and the broad pattern of unexpectedly early massive galaxies remains. Standard galaxy formation models calibrated to lambda CDM expansion history struggle to produce such massive objects so quickly. Stars need time to form, gas needs time to collapse, galaxies need time to assemble through mergers and accretion. While these observations do not directly measure the Hubble constant, they add to a growing body of evidence that the early universe may have been different from what lambda CDM assumes in certain details. If galaxies formed faster or more efficiently than expected, perhaps because the early expansion rate was slightly different, or because the physics of gas cooling and star formation operated under conditions not fully captured by current models, it could hint at modifications to early universe. Physics that would also affect the predicted expansion rate derived from the cosmic microwave background. Webb's observing programs targeting the Hubble tension are ongoing and expanding. Additional Cepheid observations in more supernova host galaxies will continue to reduce statistical uncertainties and test whether the current result holds as the sample size grows. Deeper TRA-GB and JAG measurements in more galaxies will test whether all three distance indicators converge on the same distances, a critical consistency check. Cross-comparisons between methods applied to the same galaxies will tighten the web of mutual validation that supports or undermines each rung of the distance ladder. The telescope also opens new opportunities for entirely independent distance measurements that bypass the traditional distance ladder altogether. Webb can observe gravitational lensing systems with improved precision, potentially resolving ambiguities in the lens-galaxy mass models that have limited the accuracy of time-delay cosmography. It can study surface brightness fluctuations, the pixel-to-pixel variations in the smoothness of galaxy light caused by the statistical distribution of unresolved stars at distances previously inaccessible, providing additional cross-checks on the distance scale. It can characterize the environments of Type I supernovae in greater detail, testing whether supernova standardization depends on host galaxy properties in ways that current corrections miss. Each of these programs adds a thread to a fabric of evidence that will eventually either reveal the source of the tension or confirm that it is a genuine feature of the universe demanding new theoretical explanation. Webb is not the only instrument contributing. The Dark Energy Spectroscopic Instrument is mapping baryon acoustic oscillations with unprecedented precision. The Vera Rubin Observatory will discover tens of thousands of new Type I supernovae each year across its decade-long survey. And gravitational wave detectors will accumulate more standard siren measurements from neutron star mergers. But Webb occupies a unique position in this ecosystem because it directly addresses the question that loomed largest over the tension. Are the local measurements right? The answer, as far as Webb can determine, is yes. What Webb has done so far is best understood not as a resolution, but as an escalation. The Hubble tension is no longer a problem that might disappear with better data. It is a problem that better data have confirmed and sharpened. The question is no longer whether the measurements disagree. The question is what the disagreement means. And the range of answers to that question spans everything from residual systematic effects hiding in the geometric anchors of the distance ladder to genuinely new physics operating in the early universe that our current models fail to describe. Before moving forward, re-anchor on the core point one final time. The shock is not that Webb discovered something dramatic. The shock is that the most precise infrared telescope in the history of human civilization looked at the measurements at the heart of the Hubble tension, sharpened them with instruments a generation beyond anything that came before, eliminated proposed systematic errors that had been offered as escape hatches for over a decade, and found that the disagreement is still there, unchanged, undiminished, staring back at us with sharper resolution than ever. A supposedly stable number, the expansion rate of the universe, continues to give different answers depending on when in cosmic history you measure it, and now the instruments are precise enough that the discrepancy demands an explanation that goes deeper than measurement error. The next chapter explores what those explanations might be, what each one would cost us in terms of established physics, and why the most unsettling possibility of all is not revolution, but refinement. The Hubble tension has spent the better part of a decade refusing to go away. It has survived improved Cepheid photometry from the ground and from orbit. It has survived recalibrations of the tip of the red giant branch. It has survived the sharpest infrared telescope ever launched, an instrument that was supposed to find the mistake and instead confirmed the measurement. Now the cosmology community faces a question that is less about observation and more about interpretation. The instruments have spoken. The data are in hand. If the measurements are solid, and they increasingly appear to be, what is the universe telling us? There are two broad categories of explanation, and intellectual honesty requires treating both with care. The first category is unresolved systematic errors, something wrong with one or both measurements that has not yet been identified or adequately characterized. The second category is new physics, something missing from the standard cosmological model that causes early universe and late universe methods to produce genuinely different answers when applied to the same cosmos. These categories are not symmetric in their implications. Systematic errors would be reassuring. They would mean the universe works exactly as we thought, and we simply need to be more careful with our instruments. New physics would be revolutionary. It would mean the theoretical framework that has guided cosmology for a quarter century is incomplete, perhaps fundamentally so. The responsible approach, the scientific approach, is to exhaust the first category thoroughly before embracing the second. But responsibility also demands acknowledging when the first category begins to run out of room. Start with the systematic possibilities that remain on the table. Dust is a persistent concern, and it deserves careful treatment because its effects are subtle, pervasive, and difficult to model from first principles. Interstellar and intergalactic dust absorbs and scatters light, making astronomical objects appear fainter and redder than they actually are. The effect depends on wavelength. Shorter wavelengths like blue and ultraviolet light are absorbed more strongly than longer wavelengths like red and infrared. This wavelength dependence is captured by what astronomers call the reddening law or extinction curve, a mathematical description of how dust dims light across the electromagnetic spectrum. Astronomers correct for dust using reddening models calibrated from observations of stars with known intrinsic colours. By comparing a star's observed colour to its expected colour, they can estimate how much dust lies along the line of sight and apply a correction to recover the true brightness. These corrections are well established for the average properties of dust in the Milky Way, but they carry assumptions. The standard reddening law assumes a particular grain size distribution and chemical composition, primarily silicate and carbonaceous particles, that may not hold universally across all galactic environments. If the dust properties along the lines of Site-to-Key Cepheid host galaxies differ from what standard models assume, if the grain size distribution is skewed towards smaller or larger particles, or if circumstellar dust envelopes around Cepheids themselves contribute additional reddening with a different wavelength dependence than interstellar dust, then the distance estimates could be systematically biased. A Cepheid observed through atypical dust would have its brightness corrected by the wrong amount. If the correction is too small, the star appears fainter than it should, and the galaxy appears farther away. If the correction is too large, the galaxy appears closer. The direction and magnitude of this bias depend on the specific dust properties, which vary from galaxy to galaxy and even from sightline to sightline within a single galaxy. Webb's infrared observations mitigate dust effects significantly because infrared light passes through dust much more easily than optical light. At 2 microns, the extinction from a typical dust column is roughly 1/10 of what it would be in the optical V-band. This is one of the reasons Webb Cepheid measurements are so valuable. They are far less sensitive to dust uncertainties than Hubble's optical observations. But Webb does not eliminate dust concerns entirely. Some residual corrections are still applied, particularly when comparing observations across different infrared filters, and the corrections still depend on models that assume specific dust properties. If those models are systematically wrong in a correlated way across multiple host galaxies, a small bias could persist even in infrared data. Metallicity presents a different and arguably more stubborn concern. Cepheid pulsation properties depend slightly on the chemical composition of the star. The period-luminosity relation, the foundation of Cepheid distance measurement, was calibrated primarily using Cepheids in the Milky Way and the Large Magellanic Cloud, environments with specific metallicity ranges. When this relation is applied to Cepheids in galaxies with different metallicities, some more metal-rich, some more metal-poor, a correction must be applied to account for the compositional difference. The Yesh-Nero-ES team applies metallicity corrections based on empirical calibrations using the oxygen abundance of the gas surrounding each Cepheid as a proxy for the star's overall metal content. But the size and even the direction of this correction remain subjects of active and sometimes heated debate. Theoretical models of Cepheid pulsation predict a metallicity dependence, but the predicted magnitude varies depending on the details of the stellar models, the treatment of convection, the opacity tables used, the assumed helium abundance. Some empirical studies using Cepheids in the Milky Way suggest the correction is smaller than JWST assumes. Others using Cepheids in nearby galaxies observed at infrared wavelengths suggest it could be larger, or could even change sign depending on the photometric band. If the metallicity correction is significantly wrong, if the true dependence is steeper than assumed, or if it operates differently at the high metallicity end of the distribution where many supernova host galaxies reside, it could shift the Cepheid-based Hubble constant by 1 to 2 kilometers per second per megaparsec. This is not enough to close the entire 6-unit gap, but in a debate where every kilometer per second per megaparsec matters, even partial contributions accumulate. If metallicity errors combine with dust errors and other small biases, the sum might approach the magnitude needed. The local density environment is another systematic possibility that has received significant attention. The universe is not perfectly uniform. Matter clumps into galaxies, galaxy clusters, filaments and walls, leaving vast voids between them. If Earth happens to sit inside a region of space that is slightly less dense than the cosmic average, a modest local void, then the gravitational deceleration acting on nearby galaxies would be weaker than average. These galaxies would exhibit slightly higher recession velocities than the universal expansion rate would predict, because less matter means less gravity pulling back against the expansion. The locally measured Hubble constant would be inflated relative to the true global value. Observations suggest that such a local underdensity may exist. Galaxy surveys in our cosmological neighbourhood indicate that the matter density within a few hundred megaparsecs of the Milky Way may be 10 to 20% below the cosmic average. The outflow velocities associated with this underdensity could add a systematic boost to locally measured recession velocities, inflating the apparent Hubble constant. However, most analyses indicate that the effect is too small to fully account for the tension. Detailed modelling of the local velocity field suggests the void could contribute perhaps 1 to 2 kilometers per second per megaparsec to the locally measured expansion rate. A meaningful contribution, but far short of the 6-unit gap. Moreover, the SURE-ES team uses supernovae at redshifts high enough that the most local effects should be diluted. To fully explain the tension through a local void, the underdensity would need to be substantially deeper or more extensive than current galaxy surveys indicate, which would itself create tensions with other cosmological observations. Selection bias in the supernova sample represents yet another concern that is technically subtle but potentially significant. Type 1a supernovae are not perfectly identical explosions. They are standardized through empirical corrections for their light curve shape, how quickly the supernova brightens and fades, and their color at maximum brightness. These corrections, captured in parameters called stretch and color, transform the raw peak brightness into a standardized luminosity that is consistent enough to serve as a distance indicator. But the corrections may not capture all sources of variation. Recent studies have explored whether the properties of Type 1 supernovae depend on their host galaxy environment in ways that current standardization methods miss. Supernovae in massive metal-rich galaxies appear to be slightly brighter after standardization than supernovae in low-mass metal-poor galaxies. This mass step, as it is called, is corrected for in the SURE-ES analysis. But the physical origin of the step is not fully understood. If the correction is imprecise, if the true relationship between host galaxy properties and supernova brightness is more complex than a simple binary step, then the derived distances could be systematically biased in ways that affect the Hubble constant. Each of these systematic possibilities, dust, metallicity, local void effects, supernova standardization, is being tested by multiple independent groups using different data sets and different methodologies. None has been conclusively identified as the culprit. And crucially, each one can only explain a portion of the tension in isolation. To close the full gap through systematics alone, several independent errors would need to conspire in the same direction by just the right combined amount. Each error would need to push the Hubble constant downward by 1 or 2 units, and they would all need to operate simultaneously without being detected by the extensive cross-checks that the JWST team and independent groups have performed. This is possible. Conspiracies of small errors do occur in science, but the hypothesis becomes increasingly strained as each individual systematic is tested, constrained, and found to be too small. Now consider the second category, new physics. These explanations are speculative, and should be labelled explicitly as such. None has been confirmed by observation. None is required by the current data in the way that, say, dark energy was required by the supernova observations of 1998. But they are taken seriously by a substantial and growing fraction of the cosmological community because the tension has persisted long enough, grown precise enough, and survived enough systematic tests to warrant theoretical exploration. The most studied new physics proposal is early dark energy. This hypothesis posits that a brief episode of accelerated expansion occurred in the early universe before recombination, driven by a component of energy that behaves like dark energy but is transient rather than permanent. In standard lambda CDM, dark energy in the form of a cosmological constant becomes dynamically important only in the last few billion years of cosmic history, when it begins to dominate over the diluting matter density. Early dark energy proposes that a different, additional component of dark energy was active much earlier, around the time of matter-radiation equality or shortly before recombination, contributing perhaps 10% of the total energy density for a brief period before decaying rapidly into irrelevance. The effect of early dark energy on the Hubble tension operates through the sound horizon. The sound horizon, the maximum distance sound waves could travel through the primordial plasma before recombination, serves as the ruler that the cosmic microwave background uses to infer the expansion rate. If early dark energy caused the universe to expand slightly faster during the era before recombination, sound waves would have had less time to travel before being frozen in place. The sound horizon would be smaller. When the Planck data are interpreted with a smaller ruler, the inferred Hubble constant comes out higher, potentially matching the local measurement. The stakes of early dark energy extend well beyond the Hubble tension itself. If a transient energy component dominated a measurable fraction of the cosmos for even a brief window before recombination, it would mean the universe passed through a phase that our current models completely miss. It would raise immediate and profound questions. What field or particle produced this energy? The simplest models invoke a scalar field, similar in concept to the inflaton, that is hypothesized to have driven the rapid exponential expansion of the universe in its first fraction of a second, but with very different properties, operating at a much later epoch and at much lower energies. Why did it activate at that particular moment in cosmic history and not earlier or later? The timing is suspiciously coincidental. Early dark energy must become important near the epoch of matter-radiation equality, when the universe transitions from being dominated by radiation to being dominated by matter. This coincidence requires either fine-tuning of the field's parameters or some deeper physical mechanism that links the field's behavior to the matter-radiation transition, a mechanism that no current theory provides convincingly. And why did it decay so rapidly, vanishing from the cosmic energy budget within a cosmologically brief window? Perhaps most disturbingly, the existence of early dark energy would suggest that dark energy is not the simple, unchanging cosmological constant that lambda CDM assumes. If the universe produced one episode of transient dark energy in its youth, the conceptual barrier to imagining dark energy as a dynamic, evolving phenomenon collapses. The dark energy we observe today, driving the current accelerating expansion, might also be transient, destined to strengthen, weaken, or vanish entirely over timescales we cannot yet predict. The implications cascade outward from a single number into questions about the ultimate fate of the cosmos. Early dark energy is an elegant idea, but it faces non-trivial challenges. Fitting it to the full Planck dataset requires fine-tuning. The energy component must activate at precisely the right cosmic epoch, contribute precisely the right fraction of the total energy density, and decay at precisely the right rate. If the timing is off by a small amount, the model either fails to resolve the tension or distorts the cosmic microwave background power spectrum in ways that conflict with the exquisitely precise Planck measurements. Some analyses suggest that early dark energy improves the fit to the Hubble constant, but degrades the fit to other cosmological observables, particularly the parameter called S8, which measures the amplitude of matter density fluctuations on scales of 8 megaparsecs. The growth rate of cosmic structure is sensitive to the expansion history, and modifying that history to accommodate the Hubble tension can produce predictions for structure growth that conflict with observations from gravitational lensing surveys and galaxy clustering measurements. The improvement in overall fit from early dark energy models is not universally accepted as statistically compelling. Different statistical methodologies, frequentist versus Bayesian, different choices of prior, different combinations of data sets, yield different conclusions about whether early dark energy is genuinely preferred by the data or merely tolerated. The community remains divided, with some groups finding strong evidence for early dark energy, and others finding that the improvement is marginal once the additional model complexity is penalized appropriately. Another new physics proposal involves additional relativistic species in the early universe. The standard model of particle physics contains 3 species of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, each of which contributes to the radiation energy density of the early universe. The total radiation content is parameterized by a quantity called N effective, the effective number of neutrino species. In standard cosmology, N effective equals approximately 3.044, slightly above 3 because of subtle heating effects during electron-positron annihilation in the early universe. If additional light particles existed beyond the 3 known neutrino species, perhaps sterile neutrinos, dark radiation, or other exotic particles predicted by extensions of the standard model of particle physics, they would increase N effective and raise the radiation energy density before. Recombination. A higher radiation density causes the universe to expand faster during the radiation-dominated era, which again shrinks the sound horizon and raises the inferred Hubble constant from the cosmic microwave background. The Planck measurement of N effective is consistent with 3.44, but carries enough uncertainty to accommodate roughly half an additional species. Whether that half species is sufficient to fully resolve the tension depends on the details of the analysis and on what other parameters are allowed to vary simultaneously. Most studies find that extra radiation alone cannot close the full gap without creating tensions elsewhere, but it could contribute meaningfully in combination with other modifications. Evolving dark energy represents a broader and increasingly compelling category of proposals, and it has recently received a jolt of empirical interest that has energized the entire field. If the dark energy driving today's cosmic acceleration is not a cosmological constant, not a fixed energy density woven into the fabric of space-time, but rather a dynamical field whose equation of state changes over time, then the expansion history of the universe could differ from lambda CDM predictions in ways that affect the Hubble constant. The equation of state of dark energy is characterized by a parameter called W. For a cosmological constant, where W equals exactly -1 at all times. For a dynamical field, we could vary, perhaps starting at values different from -1 in the early universe and evolving toward -1 today, or vice versa. Recent results from the Dark Energy Spectroscopic Instrument, DESI, have injected new urgency into this discussion. DESI is a purpose-built cosmological machine, a robotic instrument mounted on the 4-meter telescope at Kitt Peak National Observatory in Arizona. Its focal plane contains 5,000 individually controlled robotic fiber positioners, each capable of swiveling to a precise position within seconds to capture the spectrum of a targeted galaxy or quasar. In a single exposure, DESI can simultaneously record 5,000 spectra across a wide patch of sky. Over its planned 5-year survey, it will measure the redshifts of more than 40 million galaxies and quasars, mapping the 3-dimensional distribution of matter across roughly 11 billion years of cosmic history, with a statistical power that dwarfs all previous galaxy surveys combined. DESI's primary cosmological tool is the baryon acoustic oscillation signal the frozen sound waves embedded in galaxy clustering measured at multiple redshift bins spanning from the nearby universe out to epochs when the cosmos was less than 3 billion years old. By tracking how the apparent size of the baryon acoustic oscillation ruler changes with redshift, DESI maps the expansion history of the universe in fine detail, measuring how the expansion rate accelerated and decelerated across different cosmic epochs. In 2024, the DESI collaboration published its first-year results, based on roughly 6 million galaxy and quasar redshifts. When the team combined their baryon acoustic oscillation measurements with supernova data from the Dark Energy Survey and the Pantheon Plus sample, along with cosmic microwave background observations from Planck, they found a mild but intriguing statistical preference for models where the dark energy equation of state evolves over time. Specifically, the data favoured a scenario where W was greater than -1 in the past, meaning dark energy was less aggressive than a cosmological constant, contributing less negative pressure and driving less acceleration, and has since crossed below -1 in the recent cosmological past, meaning it now pushes expansion more forcefully than a cosmological constant would. This crossing of the W equals -1 boundary, if confirmed, would rule out the simplest models of dark energy and point toward a richer underlying physics. The DESI result is not yet conclusive. The statistical preference for evolving dark energy over a cosmological constant was approximately 2 to 4 sigma, depending on the data combination and the parameterization chosen, suggestive and exciting, but well below the 5 sigma threshold that would command consensus. The significance also depends on which supernova dataset is included and on the specific functional form assumed for the evolution of W, introducing an element of model dependence that the community is still evaluating. But the result landed in a field primed for exactly this kind of hint. Confirmation from DESI's upcoming data releases, expected over the next several years as the survey accumulates 5 times more galaxy redshifts, would represent one of the most consequential observational results in the history of cosmology. It would transform dark energy from a bookkeeping constant into a physical entity with dynamics, a history, and a future, an entity demanding explanation from fundamental physics in the same way that the discovery of cosmic acceleration in 1998 demanded it. Modified gravity theories, frameworks where general relativity is altered on cosmological scales, have also been proposed as potential resolutions. Einstein's general relativity has passed every experimental test conducted within the solar system and in strong field environments like binary pulsars and merging black holes. But it has never been directly tested on cosmological scales spanning billions of light years. If gravity weakens or strengthens at very large distances, or if it couples differently to dark matter and dark energy than general relativity predicts, the relationship between cosmic expansion and the growth of structure could change. Some modified gravity models can accommodate a higher Hubble constant while remaining consistent with cosmic microwave background and large-scale structure observations. However, these models tend to introduce additional free parameters and face their own internal tensions when confronted with the full suite of cosmological data. Other proposals populate the theoretical landscape with varying degrees of plausibility. Interactions between dark matter and dark energy could transfer energy between the two sectors, altering the expansion history. Decaying dark matter, where a fraction of dark matter particles decay into lighter relativistic products over cosmic time, could change the matter-radiation balance. Primordial magnetic fields could introduce additional pressure forces during recombination. Non-standard recombination physics could shift the inferred cosmological parameters. None of these proposals has emerged as a clear winner. The landscape of potential solutions is vast, creative, and frustrating in its lack of convergence. Each proposal resolves the Hubble tension at the cost of introducing new assumptions, new parameters, or new tensions with other datasets. The theoretical community has not found a silver bullet. What it has found is a long list of possibilities, each of which carves out a slightly different path through the space of cosmological models, and none of which is yet demanded by the data with the authority that would command consensus. This is the state of the field as it stands today, a measurement problem that resists both mundane and exotic explanation. The systematic errors that remain plausible are too small individually to close the gap. The new physics proposals that could close the gap lack decisive observational confirmation. The tension sits in a frustrating middle ground, too significant to ignore, too ambiguous to resolve, too persistent to dismiss. What the Hubble tension is really testing is not just the expansion rate. It is testing the entire lambda CDM framework. This framework does not rest on a single assumption. It rests on a constellation of assumptions, each of which has been tested individually, but never all simultaneously to the precision that the Hubble tension now demands. Flat spatial geometry. A cosmological constant with equation of state exactly -1, cold dark matter that interacts with other matter only through gravity, exactly 3 neutrino species contributing to the radiation background. General relativity has the correct description of gravity on all scales. Standard recombination physics with no exotic energy injections. A power law spectrum of primordial density fluctuations generated during inflation. The cosmic microwave background encodes all of these assumptions. The Hubble constant derived from Planck reflects every single one. If any of them is even slightly wrong, not dramatically wrong, not catastrophically wrong, just slightly off in a way that shifts the predicted expansion rate by a few percent, the tension could emerge naturally. The discrepancy might not be about one number at all. It might be a symptom of a model that works beautifully at the 97% level, but fails at the 3% level in exactly the regime where our measurements have recently become precise enough to notice. This is why Webb's role matters so profoundly. Even though Webb has not solved the problem and was never expected to solve it on its own, what Webb has done is convert a debate about data quality into a debate about physics. By confirming that the distance ladder measurements are not obviously flawed, that the Cepheids are correctly measured, that the photometry is clean, that the proposed systematic errors do not materialize at the required level, Webb forced the community to take the tension more seriously as a potential signal of incompleteness in the standard model. That is a different kind of progress. Not a discovery, but a sharpening of the question. Not an answer, but the elimination of comfortable escape routes that allowed the community to defer the question. And the question will continue to sharpen in the years ahead. Webb's observing programs targeting the Hubble tension are still expanding. The Dark Energy Spectroscopic Instrument will release increasingly precise baryon acoustic oscillation measurements. The Vera Rubin Observatory will discover tens of thousands of new Type I supernovae. The Euclid Space Telescope will map the distribution of galaxies and dark matter across the sky. Gravitational wave observatories will accumulate more standard siren measurements from binary neutron star mergers. Each new data point will either reinforce the tension or reveal a path toward resolution. If the tension ultimately turns out to be a systematic error, a subtle miscalibration in the distance ladder that was too small to detect with current techniques, or a modelling assumption in the cosmic microwave background analysis that was slightly off, the resolution will be technical and unglamorous. Cosmologists will update their calibrations, revise their error budgets, and move on. The standard model will survive intact. But if the tension proves to be real, if no systematic error can account for it, and the disagreement persists across multiple independent methods with increasing precision, then something in our understanding of the universe must change. The standard model will need a new ingredient, a new form of energy, a new particle, a new behaviour for gravity, or something entirely unexpected lurking in the gap between 67 and 73. The most unsettling possibility is not the dramatic one. It is not a headline that reads Einstein was wrong or physics is broken. It is the quieter, more methodical prospect that the universe is gently, persistently telling us that our most successful cosmological model is an approximation, an extraordinarily good approximation that captures almost everything correctly. The cosmic microwave background, the abundance of elements, the large-scale structure of the cosmic web, the accelerating expansion. But misses something subtle, something that reveals itself only when measurements become precise enough to detect deviations smaller than 10%. Something that has been hiding in plain sight for years, masked by error bars that were just wide enough to accommodate it, waiting for instruments like Webb and surveys like DESI to bring it into focus. This is what makes the Hubble tension so compelling as a scientific story. It is not about a flashy discovery. It is not about a single dramatic observation that overturns everything we thought we knew. It is about the discomfort of precision. The better we measure, the more clearly we see that something does not add up. And the fact that the discrepancy is small, approximately 9%, 6 kilometers per second per megaparsec, makes it more troubling, not less. A factor of 2 error would suggest a clear mistake somewhere, a broken instrument, a flawed calibration, an obvious blunder waiting to be found. A 9% tension between 2 exquisitely precise measurements, each grounded in well-understood physics, each confirmed by multiple independent techniques, each surviving a decade of scrutiny, suggests something subtle and deep. Something that touches the foundations. The Hubble tension is not just a problem for cosmologists in their offices and observatories. It is a problem for anyone who has ever looked up at the night sky and wondered how it all fits together. Because at its core, the tension is about whether our story of the universe is complete. And the story we have been telling for the past quarter century, the lambda CDM model, is a hell of a story. It begins with a bang. Not an explosion in space, but an explosion of space itself. A singularity of infinite density and temperature that, in a fraction of a second, expanded faster than light, smoothed out any irregularities, and set the stage for everything that followed. That period, called inflation, is the reason the universe looks the same in every direction. It stretched quantum fluctuations to cosmic scales, planting the seeds that would later grow into galaxies and clusters. After inflation, the universe was a searing hot soup of particles and radiation, quarks and electrons and photons all mixed together in a plasma so dense that light could not travel more than a tiny distance before being scattered. For 380,000 years, the universe remained in this state, cooling as it expanded. Then, when the temperature dropped enough for protons and electrons to combine into neutral hydrogen, the universe became transparent. Light could finally travel in straight lines. That light is the cosmic microwave background we observe today, a snapshot of the universe at the moment it became visible. Over the next several 100 million years, gravity went to work. The slight overdensities seeded by inflation began to pull in more and more matter. Gas collapsed into the first stars, which then gathered into the first galaxies. Those galaxies merged and grew, forming the grand spirals and elliptical giants we see today. Throughout this process, the universe continued to expand, but gravity was pulling back, slowing the expansion down. For billions of years, the cosmic expansion decelerated. Then, about 5 billion years ago, something unexpected happened. The expansion began to speed up. Some mysterious force, which we call dark energy, started pushing galaxies apart faster and faster. This discovery, made in 1998, was so shocking that it earned a Nobel Prize. And the simplest explanation for it is a cosmological constant, an energy inherent to empty space itself that does not dilute as the universe expands. This is lambda in lambda CDM. CDM stands for cold dark matter, the invisible substance that makes up about 85% of all matter in the universe. Dark matter does not emit, absorb or reflect light. We cannot see it directly, but we see its gravitational effects everywhere, in the rotation of galaxies, in the motion of galaxy clusters, in the bending of light around massive objects. Dark matter provided the gravitational scaffolding that allowed ordinary matter to collapse into galaxies as quickly as it did. Without it, the universe would look very different, perhaps with no galaxies at all. This model, with its 6 parameters, the density of ordinary matter, the density of dark matter, the density of dark energy, the Hubble constant, the amplitude of primordial fluctuations, and the optical depth to reionization, fits an astonishing range of observations. It fits the cosmic microwave background with exquisite precision. It fits the distribution of galaxies across billions of light years. It fits the abundances of light elements produced in the first few minutes after the Big Bang. It fits the way galaxy clusters grow over time. It fits the distant supernovae that revealed cosmic acceleration. Lambda CDM is not a hypothesis awaiting confirmation. It is a highly successful theory that has passed test after test for more than 20 years. And yet, here we are, staring at a crack. A crack that appears only when we look at the expansion rate in two different ways. A crack that has refused to heal despite the most careful scrutiny. A crack that Webb has now confirmed is not going away. So what happens next? The answer depends on data that are still being collected. Webb's observing programs targeting the Hubble tension are ongoing and expanding. Additional Cepheid observations in more supernova host galaxies will continue to reduce statistical uncertainties and test whether the current result holds as the sample size grows. Deeper TRAGB and JAG measurements in more galaxies will test whether all three distance indicators converge on the same distances, a critical consistency check. Cross-comparisons between methods applied to the same galaxies will tighten the web of mutual validation that supports or undermines each rung of the distance ladder. Webb can also observe gravitational lensing systems with improved precision, potentially resolving ambiguities in the lens galaxy mass models that have limited the accuracy of time delay cosmography. It can study surface brightness fluctuations, the pixel-to-pixel variations in the smoothness of galaxy light caused by the statistical distribution of unresolved stars at distances previously inaccessible, providing additional cross-checks on the distance scale. It can characterize the environments of Type 1a supernovae in greater detail, testing whether supernova standardization depends on host galaxy properties in ways that current corrections miss. Each of these programs adds a thread to a fabric of evidence that will eventually either reveal the source of the tension or confirm that it is a genuine feature of the universe demanding new theoretical explanation. But Webb is not working alone. The Dark Energy Spectroscopic Instrument, DESI, is mapping baryon acoustic oscillations with unprecedented precision. In its first year alone, it measured more galaxy redshifts than all previous surveys combined. As DESI continues its 5-year survey, its measurements of the expansion history will become exquisitely precise, tracing how the universe's growth rate changed over billions of years. If dark energy is evolving, DESI should see it. If the sound horizon is different from what Planck assumes, DESI should detect that too. The Vera Rubin Observatory, currently under construction in Chile, will begin its legacy survey of space and time in the next few years. Every night for a decade, Rubin will image the entire visible sky, discovering tens of thousands of new Type 1a supernovae each year. This vast sample will allow unprecedented cross-checks of supernova standardization, testing whether the slight variations in supernova brightness correlate with host galaxy properties in ways that current corrections miss. With so many supernovae, even subtle biases will become apparent. The Euclid Space Telescope, launched by the European Space Agency, is mapping the distribution of galaxies and dark matter across cosmic time with exquisite precision. Its measurements of weak gravitational lensing, the subtle distortion of galaxy shapes by intervening matter, will constrain the growth rate of cosmic structure with unprecedented accuracy. If modifications to the expansion history affect structure growth, Euclid should see it. And then there are gravitational waves. The network of detectors, LIGO in the United States, Virgo in Italy, Kagra in Japan, is steadily improving in sensitivity. As they upgrade, they will detect more binary neutron star mergers. For each merger, the gravitational wave signal provides a direct measurement of luminosity distance, independent of any cosmic distance ladder. Combine that with an electromagnetic identification of the host galaxy and its redshift from a telescope like Rubin or DESI, and you have a standard siren measurement of the Hubble constant. No Cepheids, no supernovae, no cosmic microwave background, no assumptions about stellar physics or recombination, just the pure geometry of space-time rippling from a cataclysmic event. The first standard siren measurement from GW170817 had large uncertainties, but the next generation of detectors, and the accumulation of dozens or hundreds of events over the coming decade will deliver some of the cleanest measurements of the Hubble constant that science can produce. If those measurements converge on 73, the case for new physics will become overwhelming. If they converge on 67, the distance ladder will have some explaining to do. If they land somewhere in between, the mystery deepens further. The next few years will be pivotal. We are entering an era of multi-messenger, multi-instrument cosmology, where no single measurement stands alone. Each method has its own strengths and weaknesses. Each carries its own assumptions and systematic uncertainties. But together, they form a network of cross-checks that will eventually corner the truth. If the tension is real, if it is genuinely telling us something about the universe, the converging evidence from these different approaches will make it inescapable. And if it is a systematic error, that error will eventually reveal itself when one method consistently disagrees with all the others. But there is another possibility, one that is rarely discussed, but worth considering. What if the tension never resolves? What if, as measurements become more and more precise, they continue to cluster around two different values? What if Cepheids and supernovae consistently give 73, the cosmic microwave background consistently gives 67, Trögby sits at 70, and standard sirens scatter all over the place? This would be a nightmare scenario for cosmology, not because it would disprove any particular model, but because it would suggest that we are missing something fundamental about how we interpret measurements. It could mean that the universe is more complicated than we assume, that there are effects we have not even imagined that bias our measurements in ways we cannot correct. It could mean that the Hubble constant is not actually constant, that the expansion rate varies from place to place in ways that violate the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The cosmological principle is a foundational assumption of modern cosmology. It is what allows us to talk about a single expansion rate for the entire universe. If it is wrong, if the universe is not homogeneous on the scales we thought, then much of what we think we know about cosmic history would need to be rethought. There have been hints over the years that the universe might be slightly anisotropic, that the expansion rate might vary slightly in different directions. Some analyses of supernova data have found marginal evidence for a direction-dependent Hubble constant. Other analyses of the cosmic microwave background have found anomalies in the distribution of temperature fluctuations that might hint at a preferred axis. None of these hints have reached the level of statistical significance that would command attention, let alone acceptance. But they linger at the edges of the data, never quite going away, never quite becoming definitive. If the Hubble tension persists and deepens, these hints might start to look more interesting. Perhaps the universe is not as simple as we thought. Perhaps the cosmological principle, like so many principles before it, is an approximation that works well enough for most purposes, but fails when we look closely enough. For now, though, the most plausible resolution remains either systematic error or new physics. And the community is pursuing both with intensity. On the systematic error side, teams are reanalyzing every step of the distance ladder with new data and new techniques. They are testing the geometric anchors with improved Gaia parallaxes and more precise maser distances. They are investigating the metallicity dependence of Cepheids with new observations and improved stellar models. They are studying dust properties in supernova host galaxies with multi-wavelength data from Hubble, Webb, and ground-based telescopes. They are simulating the entire distance ladder from end to end, injecting known biases and seeing if they can reproduce the tension. On the new physics side, theorists are building models. Early dark energy, interacting dark energy, decaying dark matter, modified gravity, extra-relativistic species, varying fundamental constants, non-standard recombination. Each model makes predictions that can be tested with upcoming data. Early dark energy, for example, predicts a specific signature in the growth rate of cosmic structure that DESI and Euclid should be sensitive to. Extra-relativistic species predict a slightly different expansion history that baryon acoustic oscillation measurements can probe. Modified gravity models predict changes in the way structure grows that weak lensing surveys can detect. The next few years will be a shootout between these models. Most will die. Some might survive. None has emerged as a clear frontrunner yet. And through it all, Webb will keep observing. Its schedule is packed with programs designed to probe the distance ladder from every angle. More Cepheid observations in more galaxies. More TRGB measurements. More JAG stars. More gravitational lensing systems. More supernova host galaxy environments. Each new observation will sharpen the picture, reduce the uncertainties, and test the consistency of the distance scale. Webb was designed to see the first galaxies, to study exoplanet atmospheres, to peer through dust into star-forming regions. That it has become a central player in the Hubble tension debate is a testament to its versatility and to the ingenuity of the astronomers who recognized what it could do. Webb is not a cosmological probe in the same way that Planck or DESI are. It cannot map the cosmic microwave background or survey millions of galaxies. But it can do something that no other telescope can do. It can resolve individual stars in galaxies tens of millions of light-years away with a clarity that was unimaginable a decade ago. And in doing so, it can test the foundation of the distance ladder, the very foundation on which our understanding of cosmic distances rests. The Hubble tension is often described as a crisis. And in a sense, it is. A crisis is a turning point, a moment when a decision must be made. For cosmology, the decision is not about which measurement to believe. The decision is about whether to accept that our model is incomplete. For decades, cosmologists have been adding parameters to lambda CDM, tweaking it here and there to fit new observations. But the Hubble tension is different. It is not a minor adjustment. It is a persistent, well-measured, multi-method discrepancy that touches the core of the model. If the tension is real, if it is telling us something about the universe, then lambda CDM, as we know, it is not the final word. There is something more. Something beyond the 6 parameters. Something waiting to be discovered. That is the exciting part. The unsettling part. The part that keeps cosmologists up at night, because the history of science is full of moments when a persistent discrepancy turned out to be a window into a deeper reality. The precession of Mercury's orbit was a small discrepancy, a tiny deviation from Newton's laws. But it led to general relativity. The ultraviolet catastrophe was a small discrepancy, a failure of classical physics to predict the spectrum of blackbody radiation. But it led to quantum mechanics. The missing mass in galaxies was a small discrepancy, a mismatch between the observed rotation curves and the predictions based on visible matter. But it led to dark matter. Small discrepancies, when they refuse to go away, when they survive every attempt to explain them away, have a way of becoming big discoveries. The Hubble tension might be one of those moments, or it might be a mistake, a subtle error that will eventually be found and corrected. Either way, the only path forward is through better data, sharper instruments, and more careful analysis, and that path is now being walked. Webb's greatest contribution to this story is not a number, it is clarity. Before Webb, the community could reasonably hope that the tension would dissolve under sharper scrutiny. Better resolution would reveal the blending error. Cleaner photometry would shift the Cepheid distances. The high local Hubble constant would drift downward. The Planck value would remain steady, and the gap would close with a quiet sigh of relief. After Webb, that hope has been significantly diminished. The proposed errors did not materialize. The measurements held firm. The gap remained. The instruments are sharper than ever, and the discrepancy is as stubborn as ever. The measurements are real, the disagreement is robust, and the universe is not yet telling us what to do about it. The cosmic expansion rate should be a single, stable number. Measure it from the infant universe using the oldest light in existence, processed through the most successful cosmological model ever constructed, 67. Measure it from the nearby universe using pulsating stars and exploding white dwarfs, calibrated through a century of painstaking observational refinement. 73. 2 methods. 2 answers. 1 cosmos, and here we sit, on a small planet orbiting an unremarkable star in an ordinary spiral galaxy, measuring the universe with the most precise instruments our species has ever built, and finding that the most fundamental number in cosmology does not quite agree with itself. The discrepancy is not large enough to declare a crisis of understanding with certainty, but it is far too large, far too persistent, and far too well measured to dismiss. The most unsettling possibility is not that the laws of physics are breaking. It is that the universe is quietly insisting we have more to learn, not through a dramatic revelation, not through a bolt from the cosmic blue, but through the patient, maddening, beautiful insistence of a number that refuses to settle. And the James Webb Space Telescope, by turning vague mysteries into testable questions, by replacing hope with data and speculation with measurement, has given us the clearest path forward we have ever had. The answer is not here yet. But for the first time in the history of this debate, the question is sharp enough, precise enough, well-defined enough, inescapable enough, to demand one. There is a moment in every great scientific pursuit when the question becomes more important than the answer. When the act of asking, of refining, of pushing against the boundaries of the unknown reveals more about the universe and our place in it than any single discovery ever could. The Hubble tension has arrived at that moment. It is no longer just a problem to be solved. It is a window into the machinery of the cosmos that we did not know existed until we started looking closely enough to see the cracks. And what we see through that window is both humbling and exhilarating. Think about what has happened here. A generation of scientists built instruments of unimaginable precision. They pointed them at the sky and measured a number. The number should have been simple. It should have been constant. It should have told us once and for all how fast the universe is expanding. But the universe had other plans. The number refused to settle. It split into 2. And the split has survived every test, every check, every sharpening of the focus. The James Webb Space Telescope, the most powerful eye on the universe ever constructed, looked at the split and said, "Yes, it is real." The split is not a trick of the light. It is not a flaw in the glass. It is not a miscalculation. It is there. In the data. In the stars. In the ancient light. In the exploding white dwarfs. In every measurement we make, the universe is telling us the same thing. You do not have the whole story yet. This is not failure. This is progress. The Hubble tension is not a sign that cosmology is broken. It is a sign that cosmology is alive. A dead science has all the answers. A living science has questions that will not go away. And the Hubble tension is the most alive question in cosmology right now. It is the question that brings together observers and theorists, optical and infrared astronomers, particle physicists and gravitational wave astronomers. It is the question that forces everyone to talk to each other, to share data, to argue, to collaborate, to push each other toward better measurements and better ideas. It is the question that reminds us that the universe is not obliged to fit into our models. The universe is what it is. Our models are just maps. And maps, no matter how detailed, are not the territory. The territory, in this case, is a cosmos that has been expanding for 13.8 billion years. A cosmos that began in a state of unimaginable heat and density, that cooled and thinned and structured itself into galaxies and stars and planets, and eventually beings capable of wondering about it all. A cosmos that is mostly dark, mostly empty, mostly unknown. A cosmos that we have only just begun to explore. The Hubble tension is a reminder of how far we have come and how far we have yet to go. A century ago, Edwin Hubble did not know that other galaxies existed. He did not know that the universe was expanding. He looked through a telescope and saw something that no human had ever seen before, and he followed it. That is what we are doing now. Following a discrepancy, following a number that will not settle, following the data wherever it leads. And where it leads is an exciting place. It leads to the possibility that dark energy is not a constant but a dynamic field, evolving over time in ways we do not yet understand. It leads to the possibility that the early universe had extra ingredients, particles or fields that left their imprint on the cosmic microwave background. It leads to the possibility that gravity itself behaves differently on cosmological scales than Einstein predicted. It leads to the possibility that the universe is not as homogeneous as we think, that we live in a special place, a void that skews our measurements. It leads to the possibility that the cosmological principle, the foundation of modern cosmology, is an approximation that breaks down when we look closely enough. It leads to the possibility that we are about to learn something fundamentally new about the universe, something that will reshape our understanding of reality, something that will be taught to future generations as the moment when cosmology took its next great leap. Or it leads to a quieter place, a place where the discrepancy turns out to be a subtle systematic error, a miscalibration in one of the geometric anchors, an overlooked effect in the dust corrections, a bias in the supernova sample. That would be a disappointment in a way. It would mean that the universe is exactly as we thought, and we were just not measuring it carefully enough. But even that would be progress. It would mean that we have learned something about our instruments, about our methods, about how to do better science. It would mean that the next generation of cosmologists will have a firmer foundation to build on. And it would mean that the tension, by refusing to go away until we found the error, did its job. It forced us to be better. The beauty of science is that it does not matter which path the truth takes. The truth is the goal. And the truth, whatever it is, will be found. Because we will keep looking. We will keep building better telescopes. We will keep refining our measurements. We will keep questioning our assumptions. We will keep following the data. That is what we do. That is what humans do. We look at the sky and we wonder. And when the sky gives us a mystery, we do not look away. We lean in. We build. We measure. We think. We argue. We collaborate. We push. And eventually, we understand. Or we understand a little more than we did before. And then we find the next mystery. The Hubble tension is that mystery. Right now, it is the number that will not settle. It is the crack in the model. It is the question that will not go away. And we are lucky to be alive at a time when we can ask it. Lucky to have instruments like Webb and Daisy and Rubin and LIGO. Lucky to have a community of scientists dedicated to finding the answer. Lucky to be part of a species that looks at the vastness of the cosmos and says, I want to understand that. I want to know how it works. I want to know where we fit in. The answer will come. It may come next year from a new DESI data release. It may come in 5 years from a Webb observation of a distant galaxy. It may come in a decade from a gravitational wave standard siren. It may come from somewhere we have not even thought of yet. But it will come. Because the data are accumulating. The precision is increasing. The errors are shrinking. And the truth, whatever it is, cannot hide forever. The universe is vast and old and full of mysteries, but it is not arbitrary. It is not capricious. It follows laws. And those laws are discoverable. That is the faith that drives science, not faith in a particular model or a particular theory. Faith that the universe is knowable. Faith that our minds, small as they are, can grasp something of the whole. Faith that the effort is worth it. The Hubble tension is a test of that faith. It is a reminder that the universe is not required to be simple. It is a reminder that every answer we find leads to new questions. It is a reminder that the journey never ends. And that is okay. That is more than okay. That is the whole point. The journey is the thing, the asking, the searching, the wondering. The moment when the data come in and you see something no one has ever seen before. The moment when a new idea clicks into place and suddenly 100 observations make sense. The moment when you realize that the universe is even stranger, even more beautiful, even more surprising than you ever imagined. Those moments are why we do this. Those moments are worth every hour of observing, every line of code, every sleepless night wrestling with a stubborn piece of data. Those moments are what make us human. And so, as we wait for the answer, we do what humans have always done. We look up, we wonder, we measure, we ask, we keep going. The Hubble tension is not the end of cosmology. It is the beginning of the next chapter. A chapter that will be written by the data, by the instruments, by the scientists, and by all of us who care enough to pay attention. The number will settle eventually. It will become clear whether the expansion rate is 67 or 73 or something in between. And when it does, we will have learned something profound, either about the universe or about ourselves. Either way, we will be richer for the knowing. But until then, the tension remains. A gentle, persistent, beautiful reminder that the universe is not finished with us yet, that there is more to learn, more to discover, more to wonder at. The cosmic expansion rate should be a single stable number. It is not. And that is not a problem to be solved. It is a mystery to be cherished. A mystery that for now keeps us looking up. And that, perhaps, is its greatest gift.